Welcome to Ajaxar Academy YouTube channel. In this session, I am going to discuss heat transfer, problems on thermal conduction, part 3. If you like this video, please subscribe to our channel. Please share your valuable comments in the comment section. Okay, let us go to the today's session. First one. The figure shows the cross section of the outer wall of a house. The wall consists of teak wood of thickness L1 and brick of thickness L2, that is equals to 5L1, sandwiching two layers of an unknown material with identical thermal conductivities and thicknesses. The thermal conductivity of teak wood is K1 and that of brick is K2 is equals to 5 K1. Heat conduction through the wall has reached a steady state with the temperature of three surfaces being known. One is 25 degree centigrade, T2 is 20 degree centigrade and T5 is minus 20 degree centigrade. Find the interface temperatures T3 and T4. See this picture. The figure shows this cross section of the outer wall of a house. Now we will calculate the interface temperatures T3 and T4. Let us go to the solution. In this, R1 is equals to L1 by K1A. R2 is equals to L2 by K2 into A. Substituting 5L1 by 5K1 into A. So that is equals to 5 gets cancels. L1 by K1A, that is equals to R1. Now this is our wall. Temperatures T1 and T5, T2 and T3, T4. 20 degrees centigrade and T1 they given as 25 degrees centigrade and T5 they given as minus 20 degrees centigrade. Here R1, R and here also R1. In steady state, 25 minus 20 by R1, that is equals to 20 minus T3 by R, that is equals to T3 minus T4 by R, that is equals to T4 plus 20 by R1. So from this R1 gets cancels. So 25 minus 20 is equals to T4 plus 20. T3 and 20 gets cancels. So finally 25 minus 25 is equals to T4 plus 20. Next, T4 is equals to 5 minus 20. We are getting minus 15 degrees centigrade. So next 20 minus T3 is equals to T3 minus T4. We are equating 20 minus T3 by R, that is equals to T3 minus T4 by R. R gets cancels. So 20 minus T3 is equals to T3 minus T4. 20 minus T3 is equals to, substituting T4 here, minus of minus plus 15. So minus T3, 20 minus 15 is equals to T3 plus T3. So that is 2T3. 2T3 is equals to 20 minus 15, 5. So T3 is equals to 5 by 2. That is equals to 2.5 degree centigrade. So the temperatures T3 and T4 are, therefore T3 is equals to 2.5 degree centigrade and T4 is equals to minus 15 degree centigrade. Okay. Next question. In this question, a double pane window consists of two glass sheets, each of 1 meter square and thickness 0.01 meter, separated by a 0.05 meters thick stagnant airspace. In the steady state, the room glass interface and the glass outdoor interface are at constant temperatures of 27 degrees centigrade and 0 degree centigrade respectively. The given here glass conductivity is 0.8 and air conductivity is 0.08. We have to calculate the rate of flow of heat through the window pane and temperature of other surface. See the picture here. Temperatures are 27 degree centigrade and 0 degree centigrade. This is the glass outdoor interface at constant temperatures 27 and 0 degree centigrade, and glass air. This is the a double pane window consists of two glass sheets of each 1 meter square and thickness 0.01. Here these are the separated double pane window. So now let us go to the solution. Now first we are finding total thermal resistance. Total thermal resistance R is equals to T1 by K1A1 plus T2 by K2A2 plus T1 by K1A1. Now substituting values in this, we get R is equals to 0.01 by 0.8 into 1 plus T2 0.05 by K2 0.08 into 1 plus T1 0.01 by 0.8 into 1. So that is equals to here 0.01 by 0.8 into 1. 2 into 0 here 0.01 by 0.8 plus 0.05 by 0.08, that is equals to, we are getting 0.65 watt inverse Kelvin. Therefore heat current H is equals to delta theta by R. So H is equals to 27 minus 0. Delta theta nothing but temperature difference. 27 minus 0 by R, that is thermal resistance. R is equals to 0.65. So 27 by 0.65, we are getting 41.5 watts. So H is equals to 41.5. Now let us calculate the rate of flow of heat. Next one, as rate of flow is same, as rate of flow is same So H is equals to 27 minus T1 by R. So that is equals to 27 minus T1 is equals to, taking cross multiplication, R into H. So 27 minus T1 is equals to R, nothing but we are getting 0.65 into H, heat current 41.5. So 27 minus T1 is equals to 0.52. After multiplication we are getting 0.52. So here T1 is equals to 27 minus 0.52. So that is equals to 26.48 degrees centigrade. So H is equals to, now H is equals to T2 minus 0 by R. So that implies T2 is equals to R into H. So T2 is equals to 0.65 into 41.5. So that is equals to, finally we are getting 0.52 degree centigrade. Okay, next we will go to the next question. In this question, 3 rods of material X and 2 rods of material Y are connected as shown in the figure. All the rods are identical, each 1 meter long and cross-sectional area 100 cm square. At the junctions A and C, there are two sources of heat, 25 watts and 100 watts. And at B and D, there are two sinks maintained at 30 degrees centigrade and 10 degrees centigrade respectively. Calculate the temperatures of the points A and C in the steady state. Thermal conductivity of X is 200 watt meter inverse Kelvin inverse, and that of Y is 400 watt meter inverse Kelvin inverse. See the picture here. In this figure, 3 rods of material X and 2 rods of material Y are connected as shown in this. All the rods are identical, each 1 meter long, and its area of cross section is 100 centimeter square. At the junctions A and C, there are two sources of heat. One is 25 watts and another is 100 watts. At B and C, there are two sinks maintained at 30 degrees centigrade and 10 degrees centigrade respectively. We have to calculate the temperatures of the points A and C in the steady state, and thermal conductivities of X and Y they given as 200 and 400. Now let us go to the solution. Now we are calculating the temperatures of the points A and C. Theta C minus 10 by Rx Ry, theta C minus theta A by Rx plus theta C minus 30 by Ry is equals to 100. Now theta C minus 10 by L by Kya plus theta C minus theta A by L by Kxa plus theta C minus 30 by Ry, nothing but L by Kya, that is equals to 100. Now this can be written as Kya by L of theta C minus 10 plus Kxa by L of theta C minus theta A plus Kya by L of theta c minus 30, that is equals to 100. Now substituting values here, Ky nothing but thermal conductivity of the rod Y. 400 into area they given as 100 into 10 to the power of minus 4 theta c minus 10 by L plus 200 into 100 into 10 to the power of minus 4 theta c minus theta a by 1 plus 400 into 100 into 10 to the power of minus 4 theta c minus 30 by 1 is equals to 100. 10 to the power of minus 4, 10 to the power of minus 4, 10 to the power of minus 4 gets cancels. Taking common in this, then we get 4 of theta c minus 10 plus 2 of theta c minus theta a plus 4 of theta c minus 30 is equals to 100. Now multiplying 4 theta c minus 40 plus 2 theta c minus 2 theta a plus 4 theta c minus 4, that is a 120, is equals to 100. 10 theta c, 4 plus 2 6, 6 plus 4 10 minus 2 theta minus 2 theta a is equals to minus 40 minus 120 minus 160, going that side plus 160, 160 plus 100 260. So from this 5 theta c minus theta a is equals to 130, dividing with the 2. So consider this as equation number 1. Similarly, theta a minus 10 by rx plus theta a minus theta c by rx plus theta a minus 30 by rx is equals to 25. Here taking common as kx a by L, then we are getting theta a minus 10 plus theta a minus theta c plus theta a minus 30 is equals to 25. Substituting values 200 into 100 into 10 to the power of minus 4 by 1. Theta a plus theta a plus theta a, 3 theta a minus theta c minus 40 is equals to 25. Okay, 10 to the power of minus 4, here 2 zeros, here 2 zeros, 10 to the power of 4, here 10 to the power of minus 4 gets cancels. Okay, next 2 into 3 6 theta a minus 2 theta c, multiplying with the 2, here 2 into 3 6, 2 theta c minus 240 is the 80, 80 is equals to 25. Okay, next we are writing 6 theta a minus 2 theta c is equals to 80, minus 80 will become plus 80, 80 plus 25 105. This is equation number 2. Solving equations 1 and 2, we get solving equations 1 and 2, we get 5 theta c minus theta a is equals to 130, multiplying with the 2 minus 2 theta c plus 6 theta a is equals to 105, multiplying with the 5. Here multiplying with the 2, 10 theta c minus 2 theta a is equals to 260, multiplying with the 5, 10 theta c plus 30 theta a is equals to 525. 10 theta c cancels. Now 28 theta a is equals to 785. Theta a is equals to 785 by 28, that is equals to 28 degrees centigrade. Next, from first equation, from 5 theta c minus theta a is equals to 130. From this 5 theta c minus theta a nothing but 28 is equals to 130. 5 theta c is equals to 130 plus 28. So 5 theta c is equals to 158. Theta c is equals to 158 by 5. Theta c is equals to 31.6 degree centigrade. These are the temperatures at points A and C. One is 785 by 28, that is 28 degrees centigrade, and other is 31.6 degree centigrade. Okay, next. In this question, three identical rods A, B, C, D and PQ are joined as shown in figure. P and Q are midpoints of A, B and C, D respectively. Ends A, B, C and D are maintained at 0 degree centigrade, 100 centigrade, 30 centigrade and 60 degree centigrade respectively. The direction of heat of flow in PQ is, see this picture, three identical rods AB, CD and PQ are joined as shown in figure. P and Q are midpoints of AB and CD. Ends A, B and C and D are maintained at A at 0 centigrade, B at 100, C at 30 centigrade and D at 60 degree centigrade. So now we have to calculate the direction of heat flow in PQ. So now let us go to the solution. Tp is equals to 0 plus 100 by 2, that is 100 by 2. So that is equals to 50 degree centigrade. And temperature at Q, that is 30 plus 60 by 2. So that is equals to 90 by 2. 90 by nothing but 45 degree centigrade. Since Tp is greater than Tq, so heat flows from P to Q. So the direction of heat flows in PQ is from P to Q. First option is correct. P to Q. So the heat flows from P to Q. Okay. Next we will go to the next question. In this question, two identical rods are joined as shown in the figure. The temperature of the junction in the steady state is, here we have to calculate the junction temperature in the steady state. See this figure. Here two identical rods are joined in this figure. So we have to calculate the temperature of the junction. So that is junction temperature. Now let us go to the solution. 100 minus theta by L by 3 is equals to theta minus 50 by L by 2 plus theta minus 50 by L by 2 plus theta minus 0 by 2L by 3. L gets cancels. So this 300 3 into 100 minus theta, 300 minus 3 theta, that is equals to 2 theta, 2 into 50 100 plus here also 2 into theta 2 theta plus 2 into 50 100 plus 3 into 3 by 2 nothing but 1.5 theta. So this is 1.5 theta. Next 300 plus 200, 500 is equals to 8.5 theta. So theta is equals to 500 by 8.5. Decimal representation 5000 by 85. So this can be written as 58.8 degrees centigrade. So therefore junction temperature theta is equals to 58.8 degree centigrade. Okay. Thanks for watching this video.